I'm really happy that I can present this here because I talked to some people yesterday and they were asking me, what are you doing? You disappeared. And that's the reason I disappeared, because of that. And since you probably never heard of it, so that means that we are doing this enclosed and it's a confidential thing and we couldn't talk about it until today. So I'll present that. I'll talk a little bit about it, why we are doing it now. There are some people in this room who have done this before. It's definitely not a new thing, right? Everyone knows how it works, and we have other Java implementations that do that, and there were other companies before us that did that. So this is important because this is still experimental, and we don't know exactly in what Java version we are going to deliver this and so on. So why are we doing this? I'll briefly talk about that. Then I'll lay out a little bit how our AOT compiler works and how you AOT compile stuff. Then I talk a little bit about the container format, which one we chose and why we did that. Then where we are right now, what we support, what we are planning on supporting in the future. Again, it's not tied to any Java version at this point. So, and then I have a bunch of numbers, so different slides. I tried to do as many as I could, and I hope we can talk through all of them. So why did we do that? Customers are asking for AOT forever, right? There are kind of three different forms the question is asked, and the first one is, I want my command line start up fast, and we heard that a bunch of times from Charlie. So, and then last year or the year before, Nasson was always complaining, oh, I want to reach my peak performance faster, right? And then there's this other group, they don't like de-optimizations. They don't like when their application gets interrupted when they want to do a very important trade. So these are the reasons. And over the past years, we always said, well, we have tiered compilation, and C1 is really fast. And so we tried to avoid doing it, because what most people requested was, well, if I start up my application and it took me 20 minutes to get there, why can't we just take that code that C2 produced and serialize it down to disk and use that? That's kind of the naive approach people outside suggest. And it sounds easy, but it's not.
Deserialization is always slow no matter what.
Well, but the main problem is that you have different phases in your application startup. And C2, it emits a lot of uncommon traps and de-optimization for things that haven't been executed or are not hot. And so if you would technically, I mean, we never tried it, but that's an assumption. If you would serialize down the code you have and you start up your application, you would de-opt like crazy all the time. So all the improvement to get quicker to peak performance is gone. So you need a different approach here. And we think that the solution is static compilation, basically. One thing I want to mention here is also, if you would serialize the code cache down to disk, you have problems with the class loading order and things like that, because it all needs to be loaded in the same order, and that's pretty impossible. So we decided to try to write everything in Java because it's easy. We basically done that, except the part that writes the container. And we did that. We're using libelf now because we started out, we didn't have a lot of time, and we started out using libelf because we knew, okay, it's producing the right container format, and we don't have to worry about that. And we wanted to replace it later, but we didn't have time anymore. Maybe we'll do it in the future. And we're using Graal for the code generation. And that has also a couple of reasons. One reason is that our existing compilers are very JIT-centric. You could do it with C1, right? Because C1 is compiling the whole method, but it's doing a lot of code patching, so you would have to replace that with something else. And one downside is if you would use an existing JIT compiler, you would have to, or it would just happen that you destabilize it, right? And so this way we know, okay, our JIT compilers do their work, and we have this other compiler, which, by the way, is written in Java, which is really nice, and we can just use it. And the other thing, and you probably heard that in a different talk by Christian Wimmer, they're using it already for AOT compilation in Substrate VM, right? So we are just taking it, and we enhanced it a little bit what we needed, and it worked pretty fine. The ultimate usage will be through JLink. So JLink will have a plugin interface, and then whatever JLink step you do, you can say, oh, okay, but if you package these classes together, I want you to also AOT compile them. We don't do that right now because JLink's not in JDK 9 yet, but that will be the end solution, and right now it's just a standalone tool. And we're doing all the optimization that Graal does, except we're not using profiling data because we're doing static compilation. We don't have any. And if we could, but at this point we don't. And we compile all paths possible, right? And that's something I said on the previous slide is we want to avoid the optimizations and uncommon traps and stuff like that. We want to compile all the paths, and we want to be able to run them. It's not always possible most of the time. And we do very, very limited inlining, and I want you to remember that when we look at the performance slides later. We only inline leaf methods that are static or final. And the main reason for that is not because we're limited by the inlining of Graal or because we haven't implemented anything that wouldn't work. It's because we didn't have time yet to figure out a good inlining policy. And if we turn on the inlining policy that Graal has, compilation times shoot through the roof, and it's you waiting hours because you don't have profiling data, so it's inlining everything. And that just doesn't work. So
is there any kind of static profile that you could use to cheat to get?
We could, yeah, of course, yeah. I mean, it depends on what you are compiling. If you do a training run or something like that, yeah, sure, you can inject profiles. So the AOT compilation will have two different modes. One we call tiered AOT, and the other is non-tiered AOT. So the tiered AOT generates simple profiling code. It's the same as in a tiered compilation system. I don't know. We have 4 different tiers, right? And a tier 2 compile is a C2 compile as a C1 compile with simple profiling. It's basically the same. So we produce that code, and then when we hit the thresholds, invocation counters or backedge counters, we'll recompile with C1 first, which sounds weird, but the reason is the simple profiling doesn't produce type profiling. We only have counters, but we also need type information. And so we compile with level 3 first, get full profiling, and then we let C2 do its job. And if we would generate a tier 3 type of code, which is with the full profiling and type profiling in, it would be just too big of a performance hit because in a tiered system, you run in the interpreter first. Not very often, it's like 100 invocations or something like that, but it's still enough to know, yeah, this is kind of warm, hot, right? But in the AOT world, you run everything compiled, and you run this this method that only is executed once, and you're producing all that profiling data that you don't need. So we stick with the simple one. And the non-tiered mode is you're running on AOT code only. So no profiling's going on. It's basically what C1 would produce, right? You don't have too many uncommon traps, you try to compile all the paths and you run on that. And that's interesting for the high-frequency trading, for cloud, because you can share code, and for embedded, where you can't, for example, JIT compile, or you're restricted by memory. JIT recompilations can happen if for some reason you hit an uncommon trap or de-optimize for whatever reason. We've seen that, so it happens. You could, there are ways to get rid of that if you really can't do JIT compilations, but this is what you'll see later. So the container format, we decided to use shared libraries. A while back, John and I were talking about this, and John always said, we should use shared libraries. And I said, well, it's really a lot of work to implement that, and so on and so on. So, for example, class data sharing, right? They're using their own proprietary format. They're serializing the thing down to disk, and then they load it back in at the same address, and everything's laid out and perfect. And it works on all the platforms. But it's really a trade-off of a well-known format versus you spin your own. The pros are, don't do what other people have done before. We don't need additional loading code in the JVM. That's a plus, right? We just DL open it and DL sim it, and there we are. All the existing tools just work, right? You can inspect the library. You can use GDB. Suddenly, you really have stack frames in GDB. Wow. And the last point is the point that John always pointed out. It's operating system engineers have spent years and years in optimizing loading these. And we see that later. Libraries can get really big, and we need them to load fast. If you, coming back to app CDS, to CDS, it's definitely faster to map it to an address, right? Because you're just mapping and it's there. You don't have to do any relocations. But the problem with that is it doesn't always work. And this has to work all the time. So we need pick code, we need relocations, we need that stuff working. And so we would have just done the same thing that shared libraries do today without help from the operating system. So we chose that. The cons is we have to do it for every operating system. That's really annoying. And it might not be as flexible as if you do your own, right? With your own format, you can do all the hacks all day you want. With an existing format, you try to find ways to make it work. And so far, we didn't hit anything that didn't work. So we were pretty happy with the choice. So what's the current status? Mainly because of the container format, we're only supporting Linux at this point. And so we, as I said earlier, we're using libelv. Christian just asked me, so what are you doing in Windows? I said, yeah, well, so we only support Linux 64-bit at this point. And what we support, we try to compile other things as well, but what we have tried to really support is the java.base module. So, because that one's used by everything that starts up, right? So if we can compile that and get some performance improvement out of this would be perfect, because then every application kind of has an advantage. And it's a new compiler after all, right? So Graal has been around for a while, and it has been used in different scenarios and so on, but it's never been a production compiler. And we're using it in a different way. Graal was tested, it's around for a couple of years, right? And it has been tested for a couple of years, but only in a JIT configuration. It was never really tested besides substrate VM in an AOT setting. So testing is really crucial here. That when we compile java.base, we have to run basically everything again on an AOT compiled java.base library. Compiling custom applications will probably be experimental in the first version because we don't have experience with it, right? It's the same as if you would introduce C3 tomorrow. You wouldn't come out with a version and say, oh yeah, every customer can compile everything. We need an experimental period where people can try it out and say, yeah, it works for me, or no, it doesn't, and so on and so on. We have many applications inside and testing frameworks and stuff inside Oracle, but it's only a tiny fraction of what code is out there. So, but we want you to try it, right? So we'll find a way to get the code to you, and there. So, as I said, right now it's a commercial feature.
Is that commercial for who builds the binary or who runs it?
I think, I don't know, run probably.
Yeah. It's a commercial feature. It will be in Oracle JDK builds. I'm not an attorney, but I believe the license says something along the lines of it is free for developer use. So
Yeah.
play with it to your heart's content. You want to deploy it in production, that's a different story.
My question was more subtle, like if I write a command line tool and shift it to put it on Maven Central, is that allowed? I don't know. Anyways.
Let's talk later.
Yeah.
We have specialists for these questions. So in the future, what we're planning to do, I mean, yeah, we need more platforms. If we want to make that a standard feature of the Java platform, and when we compile Java database, we want it on all the platforms, right? We want to compile more modules. I was looking around a little bit, and Java database is the obvious one. I've seen that Java.xml is used quite a lot for starting up the application, right? You're reading in XML files, configuration files, things like that. I don't know about logging, maybe. And the first two, you will see later in the slides. So I've compiled them, they work, but I don't know if we are going to support them in the first version. JDK compiler would definitely be helpful. If Java C is just a tiny little bit faster, it would help. It would benefit everyone. Nashorn, yeah, why not? But we'll see.
Appreciate it.
What?
We would definitely appreciate it because the initial. So when you start a Nashorn, a JavaScript program through Nashorn, there is always aside from initializing the JVM, you also need to initialize all the
Right.
Nashorn runtime infrastructure. So
Yeah.
we cannot cut down on that, and you can cut down on that.
We can a little bit. I have one benchmark with Nashorn, so we want to support custom applications, right? We want customers to be able to compile their own application. That's the goal. And then, as Marcus mentioned, we want to feedback profiling information because that makes it faster, especially in a non-tier case. And I'm again thinking about the high-frequency trader guys, right? They know exactly how the application works. They do a training around this. They save their profile and recompile it in a non-tiered way, and that would be perfect. But we don't have that yet. Okay, numbers. So these are, it's a 4-core machine, and the interesting thing is that there is one C1 compiler thread and 2 C2 compiler threads. So there's basically, if you start up something that compiles a lot, you only have one thread left for your application. It's really unfortunate. I don't know if you can see it. We are 1 millisecond slower. It's really annoying. And when we started out with that, working on it, I haven't looked in a long time, but back in March or something, Hello World was 500,000 bytecode instructions executed in the interpreter, right? And so we were working on this and working on it. I thought, it should get faster, right? And it never did. And the really annoying part was the more we compiled, all we won with making up, not executing it in an interpreter, we lost the time because the library got bigger. So you have more methods in the library. When you search for a method, it takes longer to load it in. So we wanted to be fast in Hello World. It would have been amazing, but it's not the case. On the other hand, Java C, this one is compiling hello world.java, basically, right? It's a small thing. It does something. So we have Tiered C1, which is C1, you know, with tiered stop at level 1. Then this is a regular tiered system. Non-tiered is both java.base and the application compiled in a non-tiered way. And tiered is both java.base and the application compiled in a tiered way. So as you can see, the non-tiered is faster than the tiered one because you're not executing the profiling code. But this is a 30% improvement, which is really nice. And on the next slide, and the important part is the tiered aspect. So you can still hit peak performance with that because you're producing profiling information. And we see the same with Nashorn. It's also a 30% improvement. That's, I think, executing an empty JavaScript file, which is really nice. I wanted to have that on Hello World, but you know. So this is JavaC compiling things I found. So we are JVMC. I don't know if you heard of this. This is something that we're integrating soon, and it had 200 classes. I thought, okay, that's cool. I'll try that. We are faster than a tiered system, but slower than C1. Here it's 357 classes, so it got worse. And the thing that's really annoying is this: why is C1 so fast? I don't know. I haven't benchmarked JavaC in a long time. I don't know if that was always the case or it's a regression or something. I don't know. So we're getting slightly slower here, and we're not exactly sure why this happened. And you'll see that later on another slide as well. I think it's because of the heuristics we're using. So we tried, especially for this presentation here, we tried to optimize startup performance for applications. And then it comes down to what are you profiling? And Igor, he made a change that we are not profiling very simple leaf methods because we thought, all right, if they're probably inline somewhere else or called from somewhere else, and so we don't have to profile them. And that's I think that's it, but we're not exactly sure. So at one point, yeah.
For many years, JavaC's run faster than C1.
Okay, good. So, but still, so this is annoying, but we can get rid of that. Especially on a later slide, I know that we hit exactly the same peak performance with a tiered AOT. So it's just a matter of finding out why that's the case. And then yesterday, I got an email from one of our performance engineers, and they have their own. They know doing benchmarking way better than I do, right? And so they have set up all their systems. And so he sent me this one where JavaC, and I think it's a JavaC of JDK 9, is compiling the source code of a 7 JavaC. And then suddenly tiered was faster than C1. So I don't know why. I don't know anything about this, so I have to talk to him why that's the case. It might be lambdas, or I have no clue.
Well, it's a much bigger sample. Right. JavaC is many more class files.
But I'm compiling JDK 9 JavaC here.
Oh, okay.
Yeah, that's the JDK compiler module here.
Right.
360 classes. I don't know if JavaC from Java 7 was bigger or different. Yeah.
Lambdas for sure are slower to compile.
Okay.
And so what, you were using JavaC 8 to compile JavaC 7?
No, JavaC 9 to compile JavaC 7.
Yeah, well, more or less the same. Okay. Yeah, the implementation of JavaC.
Yeah, you should know why that's the case, right? You should
Yeah.
know.
Yeah, different .com, more complex.
Okay. So yeah, we have to look into that. I mean, it's definitely encouraging that this is faster. It's just a matter of finding out why the other one's not. And then, JRuby. It took me a long time to collect all these numbers. So the leftmost one is their dev thing they are doing, and then they turn off their JIT compiler and things like that. So that's the fastest you can get today. And then I have tiered C1, tiered C1, C2 basically, and then 2 non-tiered ones. And this is interesting because of what I said earlier. The first version will not officially support compiling custom applications, right? So I'm showing this number too. What could you gain by just compiling java.base? And this is the tiered AOT thing. So Tom and Charlie, they told me, oh yeah, try disable champs because it's basically doing no JRuby stuff. It's only Java, less. So you can see with the non-tiered version, we are faster than the dev one. That's actually encouraging that the tiered one is exactly as fast as the dev one. Yeah, and you'll see on the next slide why. So here again, the non-tiered one is faster. We're getting slightly slower here. Oh yeah, I probably should point out that one as well. So you get some improvement compared to a regular tiered run. It's not that much, a little bit. So the first version will help you in a way, but what you really want is to compile your own application. And that one's nice. So this is, how many gems were there? Like
50, 60, something.
Yeah, okay, so they said that's important. I don't know why, but that's really nice compared to this guy. And the reason why this is nice is this slide. So I took Bench 9000 and I run the classic benchmarks. And you can see the first bar is their dev version, which is kind of not so fast because they turn off their compiler. And the yellow one, which was always faster in their startups, compare the yellow one to the first one. So we're about 2x, sometimes more, faster in the peak performance then. And if you do tiered AOT with both Java.base and JRuby, you'll always hit the peak performance of, which color is that? The third one, yeah.
Can you describe the vertical axis? Is it time or is this score?
No, it's score.
Okay.
This is the
Higher's better.
higher's better.
Yeah.
I've never used Bench 9000 before, so it's kind of, it prints the time when it runs and then it calculates a score. I don't know how.
On the previous
score is
slide, it was
higher
time.
is better.
Higher is better, yes.
Okay, thank you.
Sorry. So we want to compare the third column, this guy, to the last one, because that's what we either lose here in that case, but usually gain compared to a regular tiered run. And you've seen before, I think the improvement of a regular tiered startup versus this guy is 15%, if I remember correctly, 15 or 16%. So you start up 15% faster, but you reach the same peak performance. Okay, that was that. Yeah, it looks pretty good. And Charlie said that for development, the peak performance is not that important, so that the yellow one would be sufficient for developers. Yeah. So that's pretty nice. So then I did a spec JVM 98 run, mainly because it's a very short-running benchmark, and I wanted to see, are we faster on the first iteration, and where are we after the fifth? So I just picked one. So you can see the first one is a tiered C1, C2, and then we are interested mostly in the yellow one, which is tiered AOT. We are, except one, Jack, we are fast. I couldn't run JavaC because it just breaks all over the place. We are faster in the first iteration. And then when we go to the fifth one, we are slightly slower, which is about the same as I was talking before. It's this 5 to 10% that we lost somewhere. So I'm pretty sure if we can fix that problem that we hit the same performance. Is there anything else? Yeah, maybe not in this one, but with the spec benchmarks, it gets interesting to also look at the non-tiered thing to get an idea if you're not recompiling, what performance can you expect. So you see, yeah, sometimes you lose a little bit or a lot. But there's a better one, this one. So spec JVB 2013, this is 10%, and this is 5. So these are the 10% we're losing somewhere. But I remember, and I could have pulled out the old numbers, but I didn't. I remember doing this in June, and in June we had the same peak performance. So I remember that. The interesting thing here is non-tiered. So how much compared to a tiered system are you losing if you're only running on tiered AOT code? This might, I didn't look into it, this might recompile something because it deopts, could be the case. But on the other hand, as I said earlier, you should remember what inlining we're doing now. So these I think it's 20 or 25% you're slower. That's what you can expect. What we're inlining basically nothing. And with that, we can see that on a later slide. Escape analysis basically doesn't work, right? We're inlining nothing. So that's what you can expect. High frequency trader guys. That's for you. And so I also looked into, I used spec JVB because everyone knows it. It's not a perfect example because it's not a lot of code. I can't remember how much it is, but the char files, I mean, there are many char files, like 20 or 30 char files that you compile. And actually, when we compile, oh yeah, the previous slides was with, I think I didn't state that, it was java.base and spec AOT compiled. We compile everything, so we didn't go through the trouble figuring out what do you actually need to AOT compile. So we're compiling just everything because it's easier. And so if you do a JVB 2013 run, that's the code cache usage, and it's well, let me see. Non-end methods, the tiny little thing down here, that's basically the interpreter and some adapters, and then you have the profiled end methods, which are C1 compiles, and then these are your C2 compiles, the ones you want that are fast. And if you use a non-tiered AOT, you get down to this. If you do tiered, there's not a lot of change here. You basically end up with the same, a little less, but so I didn't put it on here. It doesn't make any sense. But so one thing you can see is we're definitely compiling something. And this can be de-optimizations, or what I actually think it's some reflection stuff, because we're spinning bytecodes. And
we also not compile, I mean, you compile everything, some methods.
Right, yes. Yeah, so with some methods we can't compile for one reason or the other. And so that might be the case as well. So you save about, I think it was 22 megabytes of your code cache if you run one instance. And this is just a number of blobs. So again, this down here is only adapters, and these are your compiled methods. So this was like 8,000, and you get down to 2,000. And these are the libraries. So libjava.base, so that's what it's called. It has 44,000 methods compiled in it. Clearly, spec JVB doesn't need all the 44,000, right? But we need some kind of analysis that figures out which ones do we actually need to compile to get that size down. But it's about 100 megabytes, that one library. And the dark part is the read-only part. That's the one you can share. And the other thing is, all the GOT relocations and all that stuff. And this is spec JVB with all the dependencies that are in the lib directory. It's combined, it's 40,000 methods. It's really a lot. I don't think everything's needed especially from the dependency libraries. And this one is, I think, like 85 megabytes. Most of it can be shared. So if you, or if we have a way, an analysis to figure out what we actually need to compile to get you to the speed you want, you can, and you run multiple instances of the same application on the same machine, you can share all that code, save all the 22 megabytes of your code cache, and then at X amount of instances, you definitely save memory.
Hey, Chris?
Yeah.
How big was libjruby?
It has more methods than java.base.
Yeah.
It's like 50,000 or so. Yeah. So it's 120 megabytes, something like this.
Okay.
But again, especially with you guys, I didn't know what to compile.
Right. Yeah,
There's
small portion of that that's actually.
yeah, I'm sure there's maybe only some packages that you need to compile it, but I compile everything.
Sure.
You get millions of exceptions when we try to compile JRuby because of all the JFFI stuff and the static class initializer to look for files that don't exist and things like that. It's funny, but. So I wanted quickly to show you this as well. It's kind of an odd use case because no one of you will ever do something like that, but I think it's interesting to show that we can speed up the bootstrap of Graal. And for you who don't know what a bootstrap is, so Graal is written in Java, right? And if you turn off tiered, Graal is the only compiler in the system. And so basically, when you schedule a compilation with Graal, it starts doing it. It starts doing it interpreted. But while it's doing it, it's getting hot, and it compiles itself, right? And so a bootstrap is basically scheduling all the java.lang.object methods for compilation and waiting for all the compilations to be done. So that means it mostly compiles itself and a couple methods you scheduled. So this takes on a machine, the one machine I said, like with 4 cores, and it uses all the cores to compile. It takes 28 seconds to do that. If you do a non-tiered mode, which is C1's kicking in first, compiling Graal itself, and so on, you get down to 9. And then if we AOT compile the JVM CI, which is the interface, and Graal, we get down to 263 milliseconds. So, and we compiled 3 methods. These are the java.lang.object methods. Why 263? Shouldn't it be like only 5 or 1? The reason is you have to initialize some stuff, and that's not going away. So what we are planning to do with AOT is we want to have a static class initializer analysis, some that we can actually not only AOT compile, but completely fold away. But we don't have that yet. So you have to wait for this, and you also have to wait for class loading. And I think that's the major portion of this. There's also some time involved in the Graal initialization itself, but we could technically get rid of that, fire off, when you start up the VM, fire off a compiler thread and let the initialization do on the side while the main thread is doing something. But it's all the compiles are waiting for something, and that's the initialization part. If you do it with a Graal-only bootstrap, tiered off and all that stuff, you're waiting the same time. It's just a little longer because class initializers need to be interpreted while we have it AOT compiled, so they run faster. And I'll throw this up. And it's only, this Graal thing is, we're just experimenting with it, and we see how far we can go. And again, we are not inlining a lot. That's a major issue, especially for Graal. So I took a random da capo benchmark and looked at the first couple compilations that are happening off the benchmark itself. And this is where we are. So this is the Graal one is with the 28-second bootstrap. Right, so you get the best code that you can produce for Graal. And the other one is the non-tiered AOT, which is important because what you want is, if you have something like Graal in your system, you don't want it to interfere with your application startup. So you actually want it to compile as non-tiered, so it's not recompiling itself. So I did that. Sometimes it's embarrassing. Then these are really small methods. Like they only produced 100 or 200 bytes of output code. So they are 1 millisecond, 2 millisecond. They are OK. But as soon as it gets a little bigger, and I took this 7 because there were some 1 milliseconds in between the 11th. As soon as it gets bigger and it has more work to do, it allocates more memory. And that's because we are not inlining enough. So the escape analysis doesn't kick in, and then it's just slower. Yeah, but it's encouraging. And I think that was it.